Okay, so this is video 2 on habitat suitability models. Here we see one of the histograms in the upper right here, and what we see is this is what we're looking for in habitat suitability model as far as a good model goes. We've got habitat where Doug fir does not do well, then we've got habitat where it does well, or the higher areas of higher precipitation, and then our model curve or response curve is over that area. So this is very important, both that we have this open area where there's area that isn't good habitat, and then we have some area that is good habitat that's different. And our response curve is over the good habitat. A bad model would be where the response curve is where the species isn't. And I just want to make sure folks see that this is good, this would be bad. And this is really what we're going for, is we're going for these response curves that represent the unique area within a larger area that species does well in. Now the way we get there is very similar to what we've done earlier in the semester. The difference is we have occurrences now, up here represented by some data from one of my colleagues, Dr. Catherine Jarnovich. I believe this is purple loosestrife in Colorado. We take out and get the lat long coordinates for the occurrences. Notice there's no other response, there's no presence or other measures. And then we extract data from environmental layers as we've done in the past, in this case temperature and precipitation. We run it through a modeling algorithm. We'll look at both Hemi2 and at Maxent. That gives us our model parameters, just represented as coefficients and p-values. Those are different in Maxent and Hemi. We'll talk about that in a second. And then we can again take our environmental layers, run them through a map generation algorithm based on the model parameters, and out comes our habitat suitability map, similar to the other maps we've created, except in this case the red areas are areas of good habitat, and the green areas are not so good. And if you look at our map, it looks like it is predicting where purple loosestrife is, which is an invasive species, but there's this whole area up here in the northwest where it isn't at, and that might be an area where we'd want to monitor for it because it looks like it's good habitat. Now, measuring the performance of a habitat suitability model is a little different from other methods we've used. The most popular approach is using area under the curve, which is derived from a receiver operator characteristic curve. And this is exactly what is designed for occurrence type data, even though it came from communications success. What it looks at is the true positive rate versus the false positive rate. Okay, different way of explaining this curve, the way I like to explain it, is on the vertical axis we have the proportion of occurrences are within the model. In other words, where the model is correctly predicting the species as we go from high probability to low probability versus the sample area within the model. So it's representing this characteristic that we're looking for, where we've got a lot of occurrences, okay, that are represented within the area predicted by the model versus the rest of the area. Okay, it takes a while to think about it. Come back to this a couple times, and what happens is if we have a good model, this curve will be very high. It'll go up here. If we have a random model, it'll follow this diagonal line, and if it's actually predicting the wrong spot, the curve will go over here down and to the right. Then what we do is we measure the area underneath that curve. The ultimate perfect model, this would go straight up from 0 to 1 and then across the top, so the area under the curve would be 1 because this goes from 0 to 1 on the vertical axis and 0 to 1 on the horizontal. So in this case we now have 1 times 1, area under the curve would be 1. We never see 1, but we've seen 0.9 and some other high values. You basically want to get something above 0.5, and the closer to 1 it is, the more you have found a good model or really identified habitat characteristics and unique habitat for that species within your study area. Now the advantage of this is it's really nice measure as far as the numbers go. 1 is a perfect model, 0.5 is random. It's relatively easy to compute, so in that way it's nicer than AIC. Now the problem is it doesn't include the number of parameters, so it encourages overfitting. And also, if you want to get a higher AUC value, just increase the study area, because as you increase the study area, that's going to increase this proportion of the sample area that's within the model, and it's going to make your curve go up faster, and it's going to make your numbers look better. So we have to be careful about what we call the study area when using AUC. You can use AIC. It's not built into Maxent. However, there was a software tool that came out called ENM Tools, and a paper associated with it that showed how to compute AIC. The method that I actually used came from that paper, the one I taught you in class, with the multiplying the probabilities together. There's also a presence-absence library for R that includes computing AIC for habitat suitability models, and Blue Spray has it built in as well. Question is, which is best? And that's an ongoing question we'll talk about, and you'll deal with the rest of your careers because it hasn't really been answered yet. Now, we deal with the same issues of uncertainty with habitat suitability models we do with anything else. Experts are more accurate than volunteers. A lot of the data we get that's occurrence data is from volunteers. We did a project, a couple of my graduate students, Greg Newman and Alicia Kroll, and they found 88% of the experts found an accuracy of 88% correct with experts versus 72% for volunteers. The important thing being there that they both made mistakes, so there's always this uncertainty in our data. It's also whether the species is conspicuous or inconspicuous. If you're identifying one species of invasive thistle versus 4 species that are endemic or native to that area, then it's going to be pretty easy to make a mistake. It's going to be hard to identify one thistle over the other, especially if you're doing a lot of field work in a day. If you're looking at something like tamarisk, where it's the only plant that blooms pink in our riparian areas in the desert, well, then it's pretty easy to spot. So there's going to be variance in the amount of uncertainty that we have in our data as well that will impact your models. Correcting this is a challenge. One of the areas that Maxent and Hemi do work with is one of the areas of uncertainty where you don't have the same amount of area for the environmental variation. In other words, if we look at this chart, what you see in California for precipitation is we have a lot of dry area and not a lot of wet area. In fact, we have very little amounts of wet area over here, okay, up around the 2,000 millimeters per year. Almost 2 meters of rain per year. Doesn't happen in very much of California. We have a lot of desert. So the problem is this histogram that we're seeing, the red one, is biased based on the available area. In other words, Doug fir appears to do really well here around 1,000 or 1,200 millimeters per year, and not as well up here around 2,000. However, that's because there isn't a lot of area that it gets 2 meters of rainfall. If we divide the amount of area available for Doug fir by the number of pixels it occupies, suddenly we see that actually Doug fir does really well at this higher end. In fact, we're not really representing the entire range of Doug fir. So this blue line represents dividing the number of Doug fir occurrences or pixels that have Doug fir in it by the number of pixels that are available with that same temperature. And that gives us this blue line. So that corrects for that. Now we've got a measure of how good is the habitat, or how prevalent is Doug fir in pixels that have that annual precipitation amount. And we'll talk more about this when we talk about Maxent, because that's what Maxent measures by default, as does Hemi now. Hemi, you can pick either one, but we'll talk more about it. Now, if you don't have that effect, if you do something like temperature here, where we fully represented the range of temperatures for Doug fir, it's more evenly distributed. Suddenly dividing the red by the green, or the Doug fir occurrences by the occurrences of each covariate value, it doesn't make as much a difference. So the amount of difference it makes is dependent upon the nature of the area. If the area, the environmental habitat is more evenly distributed, it's going to have less impact. Okay, so concerns with this in any spatial modeling is, are we overfitting the data, especially with Maxent? We'll talk more about that. And are we really modeling the biological ecological theory, the phenomenon that we're looking for, as opposed to the data? What does the model look like? We should be looking at it both in environmental space and geographic space. If we're using absence points, what do they mean? Is it really an absence? Is it really that that's not habitat? Same thing is true of some of the occurrences, which I don't mention here. There's redwood trees going in Sacramento, which is not where they normally occur. They've been planted there and they're maintained and watered by humans, so that would normally be habitat for redwoods. And then we need to look at analysis representation of uncertainty, and can we really model the potential distribution of a species from a subsample? I would recommend we can model a subset of its potential distribution from a subsample, but not the entire area. So with overfitting, the curve in the upper left is one from Tamaris that we did with Maxent with the default settings, and that really raised the concerns we had about overfitting. We took that to a plant physiologist, and they confirmed that that is not how Tamaris is going to respond to, in this case, temperature. It really should look something more like what we're seeing in the lower right, which is from one of the few published greenhouse experiments that we have. A lot of those are done in the commercial world, so we don't see them published as often. But that curve in the upper left from Maxent, this is the actual quote-unquote model. It has 162 parameters in it, so it's pretty overfit in my opinion. And we'll talk more about that when we get into Maxent. So what I recommend with all modeling is document the caveats. Any assumptions you have, errors, software defects, occurrences represent viable populations in the wild. So these are all assumptions that we have, and they're usually violated, right? Occurrences represent viable populations. Well, yeah, not always. Density of occurrences correlates with potential habitat. That is the key for habitat suitability to work. And it's not always the case because of other issues, especially in human modified areas. Then we have the uncertainties we have in our field and environmental layers. And remember, in Hemi's case, it uses a 256 by 256 grid for the histograms, which means it's going to quantize and have some error from that. And we'll talk more about that. This is the real thing to remember, in my opinion, is that we are modeling observations, right? We're modeling that humans have observed this species. That means we're really modeling where the species occurs with some uncertainty. We've worked with some whale data, and of course there are observations of whales when they're on the surface of the ocean, not underneath it where they spend most of their life. And of course we're not getting as many observations when they're away from the shore, so heavily biased. We'd be modeling the realized niche if the data was a complete sample for the environmental space the species currently occupies. Very important in that. So if we got all samples from the entire environmental space species is currently in, then we get the realized niche. We still wouldn't have the fundamental niche. We only get the fundamental niche if the species is covering its full range of habitats. And that's rarely the case, especially now with human modification. We've depleted species from areas where they normally occur. We've planted them in areas where they wouldn't normally occur and then watered them and cared for them. And of course, we've introduced invasive species, which are moving and filling in their habitat, or then we're fighting them back and taking them out of things that would be their spaces that would be their habitat. So this is challenging to do, but extremely important. And a couple animations for you to check out when you like, and that's it.